Wiley Plus, Chapter 14, Quiz 1. This is our very first Chapter 14 quiz, just hitting the ground with both feet moving. So this is Chapter 14, which is fluids. And what we have here specifically is the following. We have a rectangular block. We have a pink rectangular block. And this pink rectangular block is gradually pushed face down into a liquid. So we know about the block. The block has a height D. On the bottom and top, the face area is 5.75 square centimeters. And it turns out that's important to note. So if I wanted to maybe just add that in here, I know the surface area of the top. I know the cross-sectional surface area of this block. So maybe I'll try to draw that like that. And then like this. And then like this. So this is a three-dimensional block. We're living in the world of three dimensions. Volume matters. And there's my three-dimensional block. And I just drew this because I want to make sure I'm identifying the surface area. This is the surface area A. Okay, so we're gradually pushing this pink block underwater into a liquid. Is it water? I don't know. I don't think it's water. But as I push this block down into water, I have this graph of apparent weight. We should talk about apparent weight. So that's our first great discussion today. Apparent weight. Apparent weight, meaning the weight that something appears to be. Apparent weight actually has an abbreviation. Apparent weight equals W subscript apparent. And you know what it is? Do you know what the apparent weight is? It's the dry weight offset by the buoyant force. It's like when you go into Lake Michigan, well, on dry land, if you walk up to me and you try to pick me up right now, that takes some amount of effort. That takes a lot of effort. Picking me up off the ground on dry ground takes a lot of effort. However, if we are both submerged neck deep in Lake Michigan, picking me up a few feet off the ground is a lot easier. And that's because there's a buoyant force acting on it. So as this block, it's like, here's a simplified discussion. What if I have like a cup of a vase? What if I have just a container? I have a container here, and then inside the container, there's this like a golf ball. So there, or you know what? Even better, a beach ball. Here's a beach ball underwater. Beach ball. There's two forces acting on this beach ball. There's the downward force of gravity. And then here's something new. There's the upward push of buoyant force. So this is a very central term to Chapter 14. F subscript B stands for buoyant force. And that, you know what, that is important enough to spend a lot of time talking about. F sub B stands for buoyant force. And once again, you're getting the 25-cent version of the $100 YouTube lecture video. F sub B is the buoyant force. And you know what this is? This is Archimedes' principle. This buoyant force is actually equal to the weight of the displaced fluid. Weight of displaced fluid. That's Archimedes' principle right there in a nutshell. And note the following. Do you know a fluid could be a liquid or gas? There's two types of fluid, liquid and the gas. Liquids are fluids, gases are fluids, technically speaking. They both flow. And other than that, they both flow. They both take the shape of their container, but there's a lot of differences too. But that's buoyant force. This is Archimedes' principle. This is one of the giant cornerstones of fluids, fluid dynamics, fluid statics. So back to this beach ball. If you push this beach ball underwater, it's in this tank, and you push this beach ball underwater, you know from experience that this beach ball it's going to be there's going to be, the beach ball is going to be really wanting to rise. And that's because there's a very large buoyant force acting on that beach ball. Whereas the weight force isn't that great, because the beach ball is just, a piece of plastic. It's a plastic sphere, a thin plastic sphere in enveloping air. On the other hand, it's displacing a ton of fluid. So the buoyant forces, and I'll probably end up saying this like 9 times, the buoyant force is the weight of the displaced fluid. Displaced fluid. So let's just say, for the sake of conversation, let's just say this beach ball has a volume, and just again, sake of conversation, of 0.2 cubic meters. If that's the volume of the beach ball, that 0.2 cubic meters, 0.2 cubic meters, this 0.2 cubic meter beach ball will actually shove aside or displace or move out of the way the same amount of fluid. So that's why you're going to see this often. You're going to see the volume of the object, in this case, the object is the beach ball, equals the volume of the displaced fluid, which is behind, if you've ever heard of like some body fat immersion test. I go climbing in. So if I go climbing into this container of water, if this is me submerged in a container of water, I'm going to displace a certain amount of volume. So this would be the volume that I displace. If I step into this tank of water, would be the volume of Chris. The volume of my body is the volume of the fluid that I displace. So if I know the volume, if I know my body's volume, and I know my body's mass, the mass of Chris's body, which is easy enough to find, then I can figure out density. Density is mass divided by volume. So if I know my mass and if I know my volume, I'm going to come up with a density. Like, I don't know what the number is, like 10, whatever, 10 kilograms per cubic meter. And then basically the thinking is, well, for a person of my height, if this is my density, that you can just do some simple calculations and you can come to the conclusion that says Chris needs to lose weight, because you know that for a person of my height, that the density should be something different. The density of my ideal density would be probably, if this is my volume and that's my mass, it probably would be like 9 kilograms. What, again, just making up numbers. So anyway, this is the whole volume displacement. So there's a lot. There's nothing new. There's nothing new in this chapter, but there's just some unique combinations. So for example, we're talking about the critically important idea of apparent weight. And you could say, well, there's nothing new here, Chris. Apparent weight is just the dry weight minus the buoyant force. And that begs the question, well, what's the buoyant force? The buoyant force is the weight of the displaced fluid. So there's really not going to be a whole lot new this chapter. There's just going to be some very interesting applications to fluids. All right. So so we're saying now, reading on, this graph gives the apparent weight of the block as a function of how much of it is submerged. So that's what this graph is saying. This is the apparent weight, as it says, versus H, which is the submersion depth. So now that we know what apparent weight is, and now that we know what the buoyant force is, which all of this is Archimedes' principle, we can look at the graph and say, well, I'm going to do my typical graphical analysis things. What are there any magical points? You would look at slope of the graph, area under the graph. You would look at inflection points, maxima, minima, and here's a crispy intersection. That's my y-intercept, and then here's another crispy intersection. So those 2 points jump out. So I'm just going to investigate. What is this point saying? This is saying at H equal 0, the apparent weight is equal to, in my case, I have 1, 2, 3, 4, 5. I have 5 boxes, and this is 0.2. So for me, if this is 0.2, newtons. Then let's see, this would be 0.5, 1, 1.5, 0.2, 0.25. All right, so this seems to be something. At h equals 0, my apparent weight is, let me change this subscript. At h equals 0, my apparent weight is 0.25. Okay. There you go. And so that's the interpretation of that point. But let's add some more interpretation. So let me keep nudging you guys. Go past the formulas. We're all going to get the right answers here. Some of you get the right answers and actually gain a deeper understanding of what's happening. Some of you, and I've been in both categories, I'm not pointing fingers. Some of you are going to get the right answers because you're going to plug in the right numbers to the formulas that I display, and you're not going to really learn. And that's such an easy trap to fall into. So it's always a matter like keep drilling down deeper and deeper. So what does this mean? At h equals 0, WA equals 0.25 newtons. This means the following. Before submersion, before the block is submerged, because h equals 0 means there's no part of this block that's submerged. Before submersion, block's apparent weight, which by the way equals the dry weight minus the buoyant force. Before submersion, the block's apparent weight equals the dry weight minus the buoyant force. And we can say this, we can say this equals 0. So this is very helpful. The buoyant force, which for the umpteenth time is the weight of the displaced fluid, is equal to 0 because there's no fluid displacement, because no fluid is displaced. It's like when you climb into a backyard swimming pool, you're displacing a lot of fluid and you're experiencing a buoyant force. But this is before you actually climb into the swimming pool, the backyard swimming pool. The buoyant force is 0 because no fluid is displaced. Okay. So that's a lot of talking. This is what I think a lot of you do this. I can tell there's still some number of our close family here. Some of you are still just in, I can tell, and I bet I could name names. Some of you are just equation processors, which is that's a hard habit to get out of. That doesn't, I mean, for me, it took me failing and running into dead ends. It took me a long time before I said, you know what, I'm actually going to have to think this through deeply, which requires a lot of time. All right. So what about this point? Well, actually, before we move on, because yep.
I need the hard truth. Am I an equation processor?
No, you are not.
Let's go.
You are not. Actually, Ali won everyone to that level, and everyone can get to that level. All right. So number one. Well, I know the following. Aha. So number one is the aha moment. The dry weight. My dry weight, W dry, the dry weight of this, what is it? It's a rectangular block. And weight is still weight. So weight is still mg. So mg, okay, that's the dry weight, equals 0.25 newtons. So that's a big deal. That's not the answer, but it's good to know the dry weight of this block. And I know the dry weight because I know the apparent weight before submersion commences. So anyway, all of that conversation goes into me saying with confidence, the dry weight of this block is mg. Let's keep going on. All right. So I'm going to look at this point. And again, this is a separator, you guys. This is a category separator. Are you the type of person who will look at the graph and have this internal dialogue to yourself until the cows come home? Because if you are, that's the place to be. This point is saying, aha, at h equals 1.5, at h equals 1.5 cubic centimeters, my block is completely submerged. So isn't it amazing what you can find from the graph? And again, you should always try to have these internal dialogues. It is important to be able to operate equations. It is. I'm just saying, if you're that type of person, you are severely limited, and that's not a permanent condition. Just keep thinking on stuff. How do I know my block is completely submerged? Because after this block has descended by, in my case, 1.5 centimeters. So now the block is completely underwater. It's looking like this. Here. That's not good. My block is looking like this. Okay, so now my block's completely underwater. And even if I drive it underwater even further, its apparent weight's not going to change, because from this point onward, the buoyant force doesn't change. So in this flatline region, I can say two things are constant. I can say the dry weight is constant for sure. Dry weight is never going to change, because dry weight just equals mass times gravity, and that's equal to a constant. The other thing I can say is the buoyant force also equals a constant, because remember what buoyant force is. Buoyant force is the weight of the displaced fluid. And after this point, after a submersion of 1.5 centimeters, apparently there's no more displacement. I've displaced all of the fluid that this block can displace. So that is another aha moment. And at this point, so I can get a lot of things from this. I can get that D value. At this point, at H equals 1.5 cubic centimeters, no, 1.5 centimeters. So that's a typo. So then I can say H equals D. So I now know the physical dimensions of this block. I know the cross-sectional area, and now I know the height, and the apparent weight at this moment, at this position, is for me given as 0.1 newtons. So there's, again, ton of conversation just about the block. Notice how little time I've been spending on chicken scratching out equations. There's a time for equations, but there's a time for thinking too. And I've been just doing the thinking part, trying to do the thinking part now. So, all right, so you know what? At H equals 1.5 centimeter, at that submersion, I have the following. I'm just going to rewrite this. The apparent weight equals the dry weight minus the buoyant force. And now let's get more specific, number 3. So the apparent weight is 0.1 newtons, yes, equals the dry weight, which is 0.25 newtons, minus the buoyant force. And here's how I'm going to write the buoyant force. Ready? It's going to be the mass of the displaced fluid times G, because of Archimedes' principle. Archimedes' principle says the buoyant force equals the weight of the displaced fluid. And you know that weight equals mg. But now we do something new, another little nuance. 0.1 newtons equals 0.25 newtons minus rho of the displaced fluid, V of the displaced fluid, times G. So this is going to be a really common substitution right here. This is Greek letter rho. That's not P. If you say P, you should hang your head in shame. That's not P, it's rho. And rho is defined as mass per volume. So this is mass density, mass per volume. So this is why we're saying rho equals M over V. And because rho is M over V, why not just say, well, M therefore equals rho times V. And if you're wondering, why are we doing this? It's like the momentum conversation. Momentum, this is P. Momentum is defined as mass per velocity. Why are you doing that? Because the answer is sometimes it's easier to deal with velocities and masses than it is with forces, because typically you can't hook up force sensors to stuff. So you can kind of come to the same findings by using mass and velocity. So that's similar here. A lot of times we have an easier path to follow if we can just deal with volumes and displacements. So that's the substitution. That's why I made this substitution right here, which you'll see this very many times. This equals mass of the displaced fluid. But wait, there's more. Number 5. Sound like an advertisement. But wait, if you order before midnight tonight, you will be able to say 0.1 newtons equals 0.25 newtons minus the density of the displaced fluid, which, by the way, is the dollar sign. So it's good to see the dollar sign. And then here's one other change: volume of the object. O for object, I guess. Volume of the object. I think I used that before. Times G. And you know what? This merits discussion. And this was the beach ball conversation I said I was alluding to earlier. The volume of the displaced fluid is equal to the volume of the object that's displacing it. So again, if this beach ball has a volume of 0.2 cubic meters, and if that beach ball is fully submerged, then in this case, the volume of the displaced fluid would be volume of the displaced fluid equals the volume of the beach ball, or 0.2 cubic meters. So if the beach ball is fully submerged, it displaces a volume of fluid that's equivalent to its own volume. So there. All right, number 6, I think actually we're kind of close, because there's the dollar sign. There's the dollar sign, number 6. All right, so I have rho, the density of the displaced fluid, whatever it is, times V naught, which is the volume of the object that is producing this displaced fluid, times G equals 0.15 newtons. Just processing. I'm just hammering on number 5. Hopefully you see how I go from step 5 to step 6. If you don't, let's talk, but that's algebra going from step 5 to step 6. Let's keep going there. This is the dollar sign. So how do I get, I'm going to get the dollar sign. Oh, this is the dollar sign. I'm going to get this dollar sign by itself, because that is the task at hand, is to figure out the density of this fluid. The density of this fluid is equal to 0.15. And we actually have to spend a lot of time doing dimensional analysis. 0.15 newtons over volume of the object times G. So with even more numbers, 0.15 newtons is in my numerator. My denominator is the volume of the submerged block. The volume of the submerged block is its cross-sectional area, A, right here, times this dimension right here, which is D. And we now know that D equals H. So it's A times H times G. Let's keep going. Equals 0.15 newtons all over A, which for me, the cross-sectional area of this block is 5.75 square meters. H is given through my incredible powers of detective work, through graphical analysis. I mean, I don't know about you, but it helps for me just to have this internal conversation. Otherwise, I'm not seeing the forest through the trees, but through my sleuthing, that height of this block is 1.5 centimeters. And then times G, 9.8 meters per second squared. Now we have a units issue. I have a unit mismatch. I have centimeters squared. I have centimeters, and then I have meters here. And then within newtons, I know a newton is a kilogram meter per second squared. So the answer, I need to express this answer in terms of grams per cubic centimeter. So I'm going to get myself from where I am now to grams per cubic centimeter. So let's do some conversions. This is centimeters. So centimeters can stay there. All right. So from, you know what I'm going to do? I'm going to get a number on this right now. So let's go to the calculator and say 0.15 divided by 5.75 divided by 1.5 divided by 9.8 is 1.77 and some change. So I get, check out this dimensional analysis, 0.01774, whatever, store alpha A. Let's put that in calculator memory location A. And then here are the units. Apparently, I have units of newtons over cubic centimeters times meters all over seconds squared. So what are we going to do here? All right. So from a unit point of view, I have a newton is a kilogram meter per second squared. There's my numerator. My numerator is a kilogram meter per second squared. Here's my denominator. My denominator is centimeters cubed times meters. This second squared right here bounces up top. So that's second squared, which is good. Look at it, cancels. Times second squared. So let's do some cancellation now and see what we have to do. So I have second squared, meters. Not bad. Not bad at all. You know why? Because this answer that I cranked out, I have 0.001774. Units, kilograms in the numerator over cubic centimeters in the denominator. So now all I have to do is convert from kilograms to grams, 1,000 grams per kg. And that's the only conversion I guess I really needed to do. And when I do that, this is the density of this mystery fluid. It's times 1,000 or 1.77 and some change. 1.774 grams per cubic centimeter. So this is our very first problem. This is fluid statics, not to be confused with fluid dynamics. That's our first answer. So there's a ton of, on one hand, there's nothing new here, but key solution elements here is this whole notion of apparent weight, buoyant force, density. What else? Buoyant force, density, is that kind of it? Yeah, I guess. Oh, and displacement. I'd say these are the 4 key elements that got mixed in to this solution. All right, so that is our very first problem. Give me a second. Let me get the next quiz warmed up. Chapter 14, quiz 2, which is 38. Chapter 14, quiz 2 is now available. It's homework problem 38. Clear the clutter. This is, so I think the first few quizzes are fluid statics, and then we do fluid dynamics as far as today's plan. All right, so please let me know if you're not seeing what I think you're seeing. All right, we have a small solid ball released from rest while fully submerged in a liquid, released from rest. And this is a graph of kinetic energy versus the density of the liquid. So this is what's going on. We have a container. We have a tank, basically. So let me use this to indicate. Here's our tank. We have a tank. This tank gets filled with liquids, various liquids. Could be water, could be oil, could be any, a bunch of stuff. And then once we have a tank filled with a liquid, we take a small solid ball, and while the ball is completely submerged, because this is where I'm reading the question carefully, a small solid ball is released from rest while fully submerged. So you're looking at a fully submerged ball that gets released from rest, and it falls. It falls according to this test. We're letting this ball fall 3.5 centimeters. So here's the 3.5 centimeter descent. I let go. This ball falls 3.5 centimeters. And this graph is showing after this 3.5 centimeter descent within this liquid, I know what the kinetic energy is. Let me just move this up a little bit. Okay, so there's 3.5 centimeters, and now the small solid ball ends up right here. Okay, so I'm just dwelling on this. That's starting from rest. So this is starting from rest. So this, if it's released from rest, which it is, it's released from rest, K initial equal 0. Starts from rest, 0 joules. K final equals, look at the graph. Look at graph. Because I'm doing this test with a variety of different fluids. This distance here is always going to be 3.5 centimeters. And then this is where our graph comes from. So if I'm reading this question correctly, we have a graph of the kinetic energy attained by this object once it has traversed 3.5 centimeters. And now we got to figure out the volume of the ball. So V of VO is the object. That's the $sign. So I'm going to start looking at, I'm going to have my deep introspective conversation about the graph. I'm going to just look at that point, and then maybe this point, and then maybe this point. But let's see what's going on here. So this is saying when rho equals 0, when the density equals 0, the kinetic energy, which I guess I could call it K final equals Ks. That's Ks. And for me, it's 1.8 joules. So that's the superficial read of this point. Even that's tricky until you just get into the mindset of saying, okay, I'm going to look at everything, with both eyes wide open. That's what that point's saying. When rho equals 0, the kinetic energy of this ball after a 3.5 centimeter descent is 1.80 joules. What does that really mean? What does rho equals 0 mean? So you know what this means. This is the ball dropped in a vacuum. What has a density of 0? The answer is a vacuum. The density of air is like 1 kilogram per cubic meter. The density of water is 1,000 kilograms per cubic centimeter. The density of a vacuum is 0 kilograms per cubic meter, or 0 grams per cubic centimeter. So, this is an aha moment. So for sure, something from the graph results from this. When dropped in a vacuum, I'm thinking this. I can't help but think this. Work kinetic energy theorem. work equals, in fact, net work. This was chapter 7. The work kinetic energy theorem was chapter 7. A whole chapter was dedicated to this. An entire lab was dedicated to this. An entire homework assignment was dedicated to this. An exam question. So this is the work kinetic energy theorem. All right, so delta K is final minus initial, and I just alluded to the fact that the initial kinetic energy is 0 because it's dropped from rest. And in this case, the final kinetic energy using, again, I'm just keying on this point, equals 1.8 joules. Interesting. All right, so can I go any farther with this? I have the network done. Let's talk about the network. As this object is falling in a vacuum, so I'm looking at this data point right here. If I'm looking at this data point, the object is falling in a vacuum. So I'm just going to erase. There is no fluid. It's just falling from that position, 3.5 centimeters down to this lower position. So there's only one force acting on this object, and that would be the gravitational force. So here's the gravitational force acting on this object. It's just going straight down. That's the gravitational force. This is the gravitational force equals mg, the mass of the object times g. I don't think I need mass of the object because there's only one object here. There's only one mass here. All right, so that's it. That's the net force. So here's the net force. Ready, set, go. That's the force. So the net force is equal to, you remember this, F dy, F dot dy. Let me do this sort of on purpose. I'm kind of backtracking and really going into a lot of sort of pretty deep detail, just as a way to remind, just as a reminder. This is the work done by this particular force. There's only one force. So I'm going to go from dot product to magnitude angle F dy cosine theta, where theta is the angle between these two neighbors, that vector and this vector. So here's the question. What is theta? Theta equals 0 degrees. Theta equals 0 degrees because I'm specifically asking what is the angle between this green force vector, which is that weight force, and this red vector right here. So which is the displacement, this red vector is basically my y vector, not g, y. Okay. What's the angle between green and red? Theta equals 0. So I can express the work done by this force as the net work done is going to equal integral from 0 to 3.5 centimeters of mg times dy times cosine of 0 degrees equals, mg is a constant, that can come out, mg integral of dy, cosine of 0 is 1, from 0 to 3.5 centimeters. And what I'm taking quite a bit of time arriving at, you guys will, I think it's obvious, you guys can figure out that, yeah, the work done by this force is basically, in this case, it is just force times distance. So I'm just saying, this is how you really would show that very formally, although informally, yeah, you know, work is force times distance. But I am getting m times g times 3.5. I guess I'll go to, I'll stick with centimeters, equals 1.8 joules. So that's it. Because again, that net work does equal the change in kinetic energy. This is the change in kinetic energy, and this is the net work done. So from this, I can get I can get mg. I know what mg is. So I'm going to, and I'm thinking I might need mg just because I can't help but think of apparent weight equals dry weight offset by the buoyant force. So I think I can find that, well, this will be the dry weight because this is falling through a vacuum. So I'm going to get just a result for mg. Ready, set, go. Number 4, mg times, and I'm going to go to meters now, 0.035 meters equals 1.8 joules. Therefore, mg equals 1.8 divided by 0.035, or 51 and some change. 51.428 newtons. And just put that in your calculator memory location A. Store alpha A. So I do know the dry weight through the work kinetic energy theorem. This is the dry weight. All right, so this proved to be a very helpful point. I guess my next consideration is this point right here. What can I say? What is my very introspective and insightful and enlightened interpretation of this point? This is saying at rho equals 1.5 grams per cubic centimeter, K final equals 0. So that's insightful, but here's some more insight. You know what that means? That means that this density, the density of this fluid, the density of this fluid is so great, the object doesn't descend. It's like if you took a pool of mercury and threw a popcorn kernel or a popped popcorn kernel on top of the mercury, or even a ping pong ball. You take a pool of mercury and you throw a ping pong ball, that ping pong ball is just going to stay on the surface. Although in this case, we're not at the surface. The density of this fluid, so let's do the proofreading. Every class is an English class. The density of this fluid, is so great. Man, what happened to my writing skills? Is so great, the doesn't. Wow, that's just flat out embarrassing, but it's not too late. The density of this fluid is so great, the object doesn't descend. The object doesn't descend. And that seems weird because isn't this a graph of like kinetic energy? But they said, they actually, I think, covered themselves. Its kinetic energy is measured when it has moved 3.5 centimeters in the liquid. And then here, if it moves, in this case, it doesn't move. With this particular liquid, whatever it is, it doesn't move. If I change to a liquid that has, say, a density of 2.5 grams per cubic centimeter, then this object is going to go like popping up. It's going to go squirting upward, rising through this fluid. Instead of it's not going to descend. It's not going to remain motionless. It's going to rise. But at this particular point, the density of this fluid is so great, the object doesn't descend. All right, so you know what that means. This is the buoyant force. My buoyant force, I now have a buoyant force. So I'm going to show that in my free body diagram. This is not in a vacuum anymore. This is now some other fluid with a density of 1.5 grams per cubic centimeter. And I can say at this moment, the buoyant force equals the weight force. If I did a Y force inventory, says the sum of all Y forces equals the buoyant force going up minus the weight force pulling down, and that's got to equal 0 because it's stationary. How do I know it's stationary? Because there's no kinetic energy. There's no initial kinetic energy. There's no final kinetic energy. So I can say that buoyant force, which is going up, is equal to the weight force going down. And I get to do this. I'm going to do my substitution. Here's the buoyant force. Rho v g. Rho of what? Rho of the displaced fluid. V of the displaced fluid. Times G equals mass of the object times G. And I actually have that. That's sitting there in my calculator memory location A. A newtons. All right. So I'm going to do one more little rewrite because I just want to stress the following. So I have the density of the displaced fluid times, here's a substitution, volume of the object. Because in this case, when fully submerged, if fully submerged, I can say the following. The volume of the displaced fluid is the same as the volume of the object. And that is our dollar sign. Okay, so that's good. I was going to say, well, what is it? And the answer is it's the dollar sign. All right, equals A newtons. All right, so I know, here's what I know. I know the value in my calculator memory location A. I know G, of course. I know rho of the displaced fluid. It's this. We're looking at the situation with this particular fluid. All right, so now the only thing I'm going to worry about now is our units, which is kind of a common thing. Number 8, the volume of this object is going to equal whatever I have sitting there in my calculator memory location A, and that has units of newtons, all over the density 1.5 grams per cubic centimeter. And I guess I'm going to convert this because I need to end up with cubic meters. So here's my conversion. How many grams are in a kilogram? That answer is 1 kilogram per 1,000 grams. And then here's another conversion. How many centimeters are in a meter? There's 100 centimeters per meter, but I don't care about centimeters per meter. I care about cubic centimeters per cubic meter. So that's my conversion factor to convert from cubic centimeters to cubic meters. So two conversions. I need to deal with 2 conversions. Here's the cancellation. Grams here cancels with grams here. Cubic centimeters here cancels with cubic centimeters here. So from a unit perspective, I have newtons in the numerator. My denominator, I have kilograms per cubic meter. I have kilograms per cubic meter in the denominator. Okay. Oh, and I forgot G. So this is what dimensional analysis did for me. It alerted me that I forgot G. So 9.8 meters per second squared. Continuing here, I've got rho. A V naught equals over rho. There's rho. So all of this is rho, and then I need G. So G is 9.8 meters per second squared. So let me get a number on this first, and then I'll do the dimensional analysis. Alpha A divided by 1.5 divided by 9.8 divided by 1 million times 1,000. All right. I get this answer, number 9. So I'm getting the right number. V naught equals And here I can glance on my screen and say, well, yeah, that is the right answer. But I need to make sure I'm getting cubic meters out of this mess. So I'm going to fight the good fight. From a dimensional point of view, I have newtons in the numerator, and in the denominator, I have kilograms per cubic meter. And then I also have meters per second squared. So I know a newton is a kilogram meter per second squared. That's my numerator. Now my denominator is kilograms over meter squared. And then second squared comes upstairs. So I do end up with cubic meters, which is a sign of health. Kilograms cancels with kilograms. Meter squared comes up here. Second squared, good. So I do the only units that survive this dimensional analysis are cubic meters. That is this is our second fluid statics problem. Okay, we're making good time. So take some time to finish up and to introspect. And again, go beyond the formulas. Be all that you can be. Go beyond the formulas. Yes.
Could I have I read the number 2. Could I have a sanity check for number 1? Because for some reason, I still did not want to work on that one. And I tried.
Where to start? What was I guess the first thing we can get mg. What was your mg value?
Let me find this real quick. 0.12.
So you got what for this right here? What was your WS value? So
that was 0.2.
So this was 0.2.
Yeah.
So this is 0.25. So just to check, you got where are we here? You've got, and then was your flat line region here? Was this flat line value also 0.1?
That was 0.08.
If this is 0.08, this can't be 0.2.
Let me take, hold up. Let me try this right.
Yeah, take a look. Keep troubleshooting on that. While you're doing that, let me
actually, I'm sorry. Could you open quiz one back up just so I can troubleshoot?
I will at the end. I will at the
Okay.
end. Let me
Okay.
let me just go forward for the time being. Let me get quiz 3 ready. Oh, and then again, I can safely say with the utmost confidence that this does spit out. So the moment I spit out cubic meters, I'm thinking, well, I probably did things right. Even if I made like a silly calculator error, I'm probably going to get almost all of the credit on an exam because you're doing the right thing. So that's the beauty of dimensional analysis. Let me work on 14.3. 14.3 is 45. Okay, so let me get that ready. Okay, that looks good. All right. I believe that chapter 14, quiz 3 is now available. It's homework problem 45. another fluid statics problem. This is what I think it looks like. Okay. This might go pretty quick, but yeah, well, we'll find. I don't know. An iron casting containing a number of cavities has a dry weight because the weight in air is considered dry weight. Although, technically speaking, the weight of an object in a vacuum is less than the weight of that same object in air, because air has a certain amount of buoyancy. Air, what is air? Did you know that air is a gas and a gas is a fluid, because fluids have two species, liquid and gas. So there's buoyancy. There is some buoyancy associated with the air through which we travel. And but we're basically kind of ignoring the fact that the air actually does exert a buoyant force, even though it doesn't. I mean, even though it is something greater than zero. Let's begin. Number one, the dry weight, W dry, of this iron casting is Mg. The chemical symbol for iron is Fe. Fe, that's the chemical symbol for iron. So that's the dry weight right here. We have a number, 5850 newtons. This is in air, which we are just taking as the dry weight. Okay. So that's something. And then we also have another data point. We have its weight in water. So we have what's called the apparent weight. The apparent weight of this casting when it's in water is going to equal the dry weight minus the buoyant force. And whatever the dry weight is minus whatever the buoyant force is, that equals 3850. 3850 newtons. Again, given. All right, so what is the total volume of cavities in the casting? So we have basically a container. We have this tank, and we fill this tank with water. And in this tank, we have a iron casting. Whatever, maybe it's an iron sphere. So just don't know what it is. So let's just call it an iron sphere. Like this. Okay. Within this iron casting, there are a number of voids. There are a number of cavities. So just think of it like a sponge or Swiss cheese. We have some number of empty spaces, voids. Again, think sponge or Swiss cheese. It's amorphous. So these are voids. This is a cavity, empty space. This is empty space. All right, so all of these cavities, all of these empty spaces add up to something. In fact, we have to find out what is the volume of all those cavities. So that is the dollar sign. The volume of all these cavities is V of all those cavities equals the dollar sign. Okay, so before still adding some visuals to my drawing here, it's time to do free body diagrams. I have the weight of this object going down. Gravity is pulling it down. I have the buoyant force going up. I don't know how they compare, but that is the buoyant force. This is the buoyant force. This is the weight force, and they oppose each other. Okay, so I'm just going to go with my apparent weight expression because I'm given the dry weight and I'm given the apparent weight. So that seems to be a lot of information. The apparent weight, so number 2, here's the updated number 2. The apparent weight equals 3850 3850 newtons. 3850 newtons equals the dry weight, which is 5850 newtons, minus the buoyant force. And here's the buoyant force, rho VG, where this is the density of the displaced fluid. This is the volume of the displaced fluid. Although I think by this time, I should be able to just say, well, the volume of the displaced fluid is in fact the same as the volume of the object. So I'll just say volume of the object times G. I don't see my dollar sign yet, so I'm going to just keep drilling down here. I have, I'll say this. The volume of the object is equal to the volume of the iron plus the volume of all of those cavities added together. And that's my dollar sign. So I finally see my dollar sign. Number 6, then, I can say, well, I'll just do this. I'll say rho, density of the displaced fluid, volume of the iron plus volume of the cavity times G. There's my rho VG equals 2000 newtons. So I'm just doing some rearranging and some algebra. I'm isolating rho VG here. And that's what I get. And there's my dollar sign. So number 7, I got to solve for, I got to isolate V cavity. So if I do a little bit of algebra here, I can see the volume of the iron, which is making me wonder, do I know the volume of the iron? I don't know. Plus the volume of the cavity equals 2000 newtons. That's my numerator, over the density of the displaced fluid, which is water. And I know the density of water times G. Okay, is that good? 2000 over rho G. All right, so let's isolate the volume of the cavity, which is my dollar sign, equals, maybe with some more numbers, 2000 newtons all over the density of water. The density of water, this is a standard, a constant. So it's 1,000 kilograms per cubic meter times 9.8 meters per second squared minus the volume of the iron. Okay, so now I have to worry about what the volume of the iron is. And the answer is I'm not given the volume of the iron, but I think I have enough information because I know in general, rho equals mass over volume. And specifically for iron, the density of iron equals the mass of the iron all over the volume of the iron. So I can isolate now, or I can rearrange for the volume of the iron, which is my last sort of little challenge here. The volume of the iron is going to equal the mass of the iron all over the density of the iron. So my iron, I don't know what the mass of my iron is, but I don't know the mass of the iron, but I do know the weight of the iron. So if I'm looking right here, I can see that the mass of the iron equals 5850 newtons all over G. So I'll just use that. I have the mass of the iron, which as mentioned is 5850 newtons all over 9.8 meters per second squared. That's the mass of the iron. That's my numerator. All over the density of the iron, which is 7.87 grams per cubic centimeter. And I have to live in the world of cubic meters because it's expecting an answer in terms of cubic meter. So here's the conversion factor. I'm going to convert by saying there's 1 kilogram per 1,000 grams. And I'm going to remember that there's 100 centimeters per meter, but then I need to cube it because I'm dealing with cubic centimeters and cubic meters. So you know what? This is a lot of crazy stuff, but I'm gonna get a volume value here and just put it in my calculator memory location. All right, so what is that? 5850 divided by 9.8 divided by 7.87 divided by 1,000,000. 1, 2, 3 times 1,000. And I'm going to double check store alpha A, I guess. Right, I am getting the same answer twice. So whatever that number is, it's now stored in calculator memory location A. All right, so now I'm good to go, I think, because step 10. Go back to number 8 and solve. And solve, because now you know everything's known here. You know everything's known because now we know the volume of the iron. Okay, so 2,000. Okay. Lots of good dimensional analysis. The volume of those cavities for me is 0.1282 and some change. Doing dimensional analysis, which is something you should do, is going to spit out cubic meters. Okay, it's 210. See you at 2:20 p.m. where I think we start to do fluid dynamics.
A question real quick. How'd you get in FCAV number 8? How'd you get 1,000?
Number 8.
Yeah,
Um,
1,000 kg over
well,
MC.
this is the density of water. This is like a no. You don't have to have it memorized, but this is a constant. Let me make this apparent. Right here, you're talking about, Ty.
Yeah.
This is the density of water, which comes from here. The displaced fluid, this is water. So the density of water is that 1,000 kilograms per cubic meter.
Okay.
So good
So
question.
that's something we're gonna have to know. I'm guessing.
No, it's something that, I mean, if you look at your exam, it's given to you on the header of your exam. So you don't need to memorize it. You just need to know to look it up when you,
Okay.
when you need it. Right.
Thank you.
Yep. Chapter 14, quiz 4, fluid dynamics. This is referring to something known as a pitot tube. Pitot tube. So a couple of pictures on pitot tubes. A pitot tube is an airspeed indicator. So if you look on jet airplanes, I mean, they're very easy to see. Let me just find a good picture of one. Well, here's one on a big old airplane. Pretty good. Here. Okay. So you see these little gizmos. They're like, look at them. They're like little tiny tubes. They almost look like handles, like you grab hold and you lift up on them. But these are pitot tubes. These are again, airspeed indicators. And that's what it looks like on a, I mean, all airplanes have. To ask yourself, how does a pilot know the airspeed of the airplane? And the answer is pitot tubes and fluid dynamics. So let me just see if I can get up. Oh, here's an up close and personal picture. Right here. Yep. All right. So this is a smaller airplane, but you can see there's a pitot tube. And again, it looks like a hand and it's covered. It's covered with this red cap just to keep it clear of debris. So it's this little tube with a very specific design. And this quiz right here, chapter 14, quiz 4, is showing you a pitot tube. The pitot tube is used to determine the airspeed of an airplane. It consists of an outer tube with a number of small holes. So right here, it's encircled. So there's a number of holes encircling this tube as shown here. And then the tube, it's a hollow tube. So then you have this passageway here. And then you have, this is a manometer. It consists of an outer tube with a number of holes that allow air into the tube. That tube is in turn connected to this U tube. It's called a U tube because it looks like the letter U, and it's also sometimes referred to as a manometer. All right, so this is our design. The other arm of the U tube is connected to the hole at A. So, all right, so we have, all right, this is what's going on. We have a manometer connected here and then here. Okay, so let's keep reading. That tube is connected to one, the other, blah, blah, blah. All right, so I covered all that. All right, so the airplane is, the airplane velocity is going this way. So here's the velocity of the airplane. It's basically like in this direction. It's in that direction. And as the airplane is slicing through the air, you can see these streamers. These have a special name. This is a good name to really bank on. These are called streamers. I think of them, well, they are called streamers. And basically they're little threads of fluid, little tiny threads of fluid. And there's a bunch of them. We're just showing like we're showing like 4 sample streamers here. And a lot of times it's very helpful to identify a streamer and use it as the basis of your analysis. So a streamer is a little thread. Streamers are little threads of fluid. And so these are streamers. And way over here, that's a streamer as well. Okay, so let's keep reading. The airplane is going in this direction, V for velocity. Now it says at point A, right here, at point A, here, it's saying there's a log jam. At point, excuse me, at point A, the air becomes stagnant. So at point A, there's just not an opportunity for the air to flow through the pitot tube. There's just this very acute log jam. All the air is jammed up. No air actually passes through this tube because the speed is just too great, and there's too much air trying to go too quickly through too small of an orifice, which is why I refer to it as a log jam, or it's stagnant air. Stagnant air means log jam. Like a stagnant pond means the water's just sitting there. There's no circulation, no flow. This is stagnant air at point A. And this is by design. These are the pitot tubes are, designed to make that happen. Okay. At B, however, the speed of the air presumably equals the airspeed of the plane. Okay. So here at B, we have, this is the velocity at B. So whatever this velocity here is going to basically be the airspeed of the plane. Okay, because if, for example, if the air is going 100 meters per second to the right, it's because the airplane is going 100 meters per second to the left. So that's how these pitot tubes are designed. Okay, so we need to figure out what's the airspeed for this situation. What's the airspeed? So now is the formal introduction to Bernoulli principle, and we're going to start with EAM. So it's the gift that keeps on giving. This is energy state A right here. I'm going to call this energy state A because I'm told about it. I'm going to call this energy state B. So let's do EAM and find our way to the Bernoulli principle in the process. All right, the energy at A plus non-conservative work. And here's the big thing. Non-conservative work is not equal to 0 in this case, equals EP. All right, so at A, there's some kinetic energy at A. There's some gravitational potential energy at A. There is some non-conservative work. And then at B, kinetic energy at B plus gravitational potential energy at B. Let me do this. Let me say, well, at A, there's 1/2 mVA squared. That's my kinetic energy. My gravitational potential energy is mGYA, and I better establish a baseline. I guess I'm going to call this my baseline. So we're back to we're back to the situation on or near the surface of the Earth. So which means I have to establish a baseline. This isn't Newton's universal law. So this is my baseline. Okay, and then there is some non-conservative work, and I'll probably spend more time talking about non-conservative work than anything else, but let's keep going. And then at B, at energy state B, kinetic energy, yes, 1/2 mv squared plus mGYB. Okay, so now what if I go ahead and divide through by volume? I'm gonna divide every term by volume. So I'm going to divide this by volume, that by volume, this by volume. I'm just going to divide through by volume. And when I do that, I get, let's see, what does that lead us to if I divide through by volume? Number 5, I get 1/2 rho VA squared. How did I get, why am I getting rho? Because right here, mass per volume, this mass variable divided by this volume, mass per volume is rho. So here's my energy analysis. Conservation of energy says 1/2 rho VA squared plus rho G HYA. Same reason, because M over V is density. Plus, maybe I better start talking about non-conservative work. Non-conservative work, and this is in the YouTube video, but just generally speaking, what if I just have some weird looking tube, like an odd looking garden hose, like that, for example. And then I have fluid. If I have fluid flowing through this garden hose, so maybe I just have I have like a sample volume of fluid right here. Okay. So as this, and there's fluid continuously flowing through this garden hose, but I'm just going to look at this sample. Let me fix that up. It's a little bit hard to. I'm just going to train my attention on this particular sample, even though it's completely full of water and it's continuously flowing. I'm basically going to look at like what's going to happen with this little sample of fluid. Well, I'm going to have pressure exerting a force on it in that direction. And then you know what? I'm going to also have pressure exerting force on it in the other direction, maybe like this. So I have these opposing pressures like that. So I have the pressure, maybe I'll call it, this is the leftward pressure and this is the rightward pressure. And they're at odds with each other. And how do I know to draw them like that? Because this is coming from the surroundings. These pressures, these two pressures come from surrounding fluid. Maybe it's the atmosphere. Maybe it's like a fish aquarium. Maybe it's the surrounding fluid in a fish aquarium, or maybe it's just from the adjacent atmosphere. But it comes from surrounding fluid. Could be a gas, could be a liquid. That's what these are referring to. So if they're equal, if everything is equal, then there's no flow. But if there's any inequality, then there's going to be some flow. So I'm going to just represent that as the work done. This is the work done by pressure all over volume. That's my left side equals 1/2 rho VB squared plus rho G YB. So this is, we're not quite in the final form of the Bernoulli equation. Let's just keep going one more step before we really step back and look at this. I have 1/2 rho VA squared plus rho GYA. And then looking at, again, this pressure, the work done by pressure. The work done by pressure, let's just talk about, well, work over volume. So let's just do dimensional analysis. What is work? Work is force times distance. Force times distance over volume. So I'll do it like this. Force is force. Distance is D. And volume, you could argue, is D cubed. Length times width times breadth. Volume has some cubic measure. Distance has some linear measure. So I'm going to write this as F over D squared times D over D, which this is the same as pressure. The definition of pressure is defined, this was defined in chapter 14. The definition of pressure is force per area. So pressure is force per area. And I'm saying through this little sidebar conversation that work divided by volume is the same as force times distance divided by volume. And we are talking about the net force. This is the net force resulting from this contest between that leftward pressure and this rightward pressure. That's what that force is referring to. Distance is the distance through which it acts. So this would be distance, the distance through which those forces act. And basically doing this, again, sidebar conversation is saying, well, okay, and I just want to double check myself. This is pressure right here. This is pressure, thanks to the definition. This equals 1. Okay, that's it. So now I'm going to finish all of this setup and say, well, all right, this is going to be plus that work, and the work is just going to be the pressure at A minus the pressure at B equals 1/2 rho VB squared plus rho G YB. And the last form, and then we actually solve this problem. All right, here's the final form of the Bernoulli equation. Ready? PA plus 1/2 rho VA squared plus rho GYA equals PB plus 1/2 rho VB squared plus rho GYB. So I went through this giant sidebar conversation so that it's very clear that the Bernoulli principle is just conservation of energy. We refer to this term as pressure energy. Pressure, maybe, you know what, I could refer to that as, you know what's a better term? I'm liking this. This is just ripped from today's headlines. I'm liking the term pressure work energy density, or pressure work density. And in fact, what is work? Work is just energy put to some use. So I'm just going to say this is pressure energy density, because work over volume is, I can think of that as just an energy density. This is kinetic energy density. This is gravitational potential energy density. So those are the three flavors of energy. You have conservative, you have conservative potential energy density, kinetic energy density, and non-conservative pressure energy density. The work done by pressure depends on the path. So anything path dependent is a non-conservative force doing non-conservative work. That's it. This is truly a cause for celebration, because now you lived through the story of how the Bernoulli principle is just conservation of energy. So as far as this problem is concerned, so it's so much better to think about it like this versus just saying, here, let me spoon feed you an equation, and then you dutifully plug in numbers and punch keys on your calculator. This is so much better than that. It just makes you a better problem solver, a more creative designer. So let's solve this problem. Number 8, I guess I'll go over here. Number 8. Well, I'm just going to keep this around. Let's go about some low-hanging fruit. Here's some low-hanging fruit specific to this problem. This whole term equals 0. This equals 0 because I have stagnant air at A. So going back to our specific situation. And you know what else? This term right here, rho GYA, is the same as rho GYB. So they basically just eliminate each other. And I'm saying that because this is a horizontal tube. Horizontal tube. Okay, because you can see it's horizontal. And you might say, well, it's a horizontal tube, Chris, but I have a streamer. I have a streamer that's changing height. So this streamer is actually increasing potential energy. This streamer is losing potential energy, but you can see the net effect is there's no change. So for every gain in potential energy, there's a loss in potential energy. So that's why we just basically consider this to be a horizontal situation, which means there's no changing of the gravitational potential energy density of these streamers. So let's go to number 8. Number 8 says the pressure at A equals, that's it, huh? The pressure at A equals the pressure at B plus 1/2 rho VB squared. Okay. We're solving for the airspeed. So let's isolate VB. VB equals PA minus PB all over 1/2 rho. So let's talk about numbers now. Is it time for numbers? Yes, I think so. Numbers.
Do you square root that?
Good one. Yes, you do. Good catch. Okay, so a pitot tube on a high altitude aircraft measures a differential pressure of 190 pascals. So differential pressure means pressure difference. So the only question I have is this the difference? Is PA minus PB equals 190, or is PB minus PA equals 190? So that's, I don't know what that answer is, but until I think about it, if we think about what the Bernoulli principle is saying, the Bernoulli principle is saying if the only thing that's changing is pressure and velocity, if height is held constant, so if the change in height equals 0, there's no change in height, meaning horizontal in this case, then if you look at the Bernoulli principle is saying the following. I'm going to write this out one more time. So PA plus so that is pressure energy density plus kinetic energy density plus gravitational potential energy density, rho g y a, and that's going to equal some constant. This is going to equal some constant. And you could say, hey, Chris, doesn't it really equal PB plus? Yes, it does, but it's constant. Whatever this amount of energy is here on the left side, conservation of energy says it doesn't change. It doesn't change. So if you keep that in mind and you say, well, what if velocity increases? You can see if this has to equal a constant and the velocity increases, if the velocity increases, then the pressure must decrease. And you know what the takeaway from that is? Fast flow goes with low pressure. And there's tons of practical examples of this. Fast flow goes with low pressure. And sort of on the flip side of that, we would say low flow velocity is associated with high pressure. Okay, so fast flow goes with low pressure, slow flow goes with high pressure. And here's just a very simple example. There's tons of examples, carburetors, but I'm going to look for a Venturi pump. Fast flow goes with low pressure. So check out this. We're not gonna watch all of it. There. So you get the hang of it. This is a Venturi pump. Carburetors work on the same principle. Basically, you're looking at fast flow associated with low pressure. So because the pressure decreases, you have the atmospheric pressure, which is what it is. But then if you have this fast flow, you reduce the pressure and you get this pump. You get this pump effect. So lots of examples. We'll demonstrate a lot of these, but that's enough of that. Let's go back to the problem. Fast flow, low pressure, slow flow, high pressure. Okay, so having said that, now let's see, at energy state A, I for sure have low flow. In fact, I have zero flow at A because of that stagnation, the logjam. So I have the high pressure. So I know I've just answered my question. I know it's PA minus PB because I know for sure my pressure at A is higher than it is at B. So this is my 190. It is in fact PA minus PB, not PB minus PA. Okay, so I guess we can solve. Let's see. You know that PA minus PB is 190. This is rho, and rho is given for me. This is the density of air. So we know everything here. Let's get an answer. 190. Oh, here's something. From a dimensional analysis point of view, VB squared equals 190 pascals. Here's what a pascal is. A pascal is a Newton per square meter because of the definition of pressure. If pressure is defined as force per area, force is newtons, area is square meters, and we now refer to this as a pascal. Pascal, or just PA for short. All over 1/2 rho. So careful with your dimensional analysis. Okay. Oops. Okay. Our first fluid dynamics problem. 14.5.
I'm getting 14,000, but it says it's wrong, and it's my pressure is 210.
Did you
And
take
I-
the square root?
You got me.
Yeah, I mean, that was your idea.
Yeah, I kind of forgot.
We're helping each other. We're collaborating. All right, so let me do 14.5 is 64. Okay. It is now 2:53. Okay, chapter 14, quiz 5. I think should look like this. More fluid dynamics. Okay. And give me, I want to check on something. So just give me another 60 seconds to maybe find something. I'm looking for an animation.
Professor, did you say you were changing quiz 5?
Nope.
Okay, because the one that's currently up on Wiley Plus is different for us than what's on yours.
Is it different for everyone?
I'm sorry. Well, I should say it's different for me, but
Is that so? I guess question to everyone. This is what I think is chapter 14, quiz 5. Is that what you're seeing on your side or no?
It's
I'm
still loading
loaded.
for me.
It's what?
It's different.
So,
It's different.
Yeah.
All right. So let me go to chapter 14, quiz 5. Chapter 14, quiz 5. Chapter 4. Let me just double check. 1, 2, 3, 4, 5. Oh, yeah. 1, 2, 3, 4, 5. You're right. It should be problem 64. It should be problem 64. Apparently, it's not problem 64. You're right. It's not. It's problem 65. Chapter 14. All right. This time for sure. Is everything else good? Yep. All right. So thanks for speaking up. And again, don't hesitate to speak up. The sooner you speak up, the better. Otherwise, it could be next Tuesday and I'm still talking about a screen that you're not looking at. Okay, so again, I wanted to find. So I'm going to let me take that minute again. I want to find, I think this is it, continuity equation. No, well, maybe this is it. Huh. Not really. Okay, so that's enough time. Let's talk through this. We have a horizontal pipe. Water flows through a horizontal pipe and then out into the atmosphere. We know a lot about this pipe. What volume of water flows into the atmosphere over 10 minutes? Okay, so here's what I'm focusing on. Here's region 2. Region 2 is right here. I have the velocity of the fluid inside. This is some interior. This is the fluid inside of this pipe is called V2. V1 is right basically here. Wait, there. Okay, so this is exposed to the atmosphere. I'm just reading the problem carefully. This is V1. I'm going to call this P1. So V1 is associated with P1, and this is atmospheric pressure. So P1 is just the atmospheric pressure. It's exposed to the atmosphere, which is again adjacent to this area here. Now V2, on the other hand, is associated with P2. And it's kind of tough to see it, I think, in this visual, but P2 is not the atmospheric pressure. The atmospheric pressure exists right here. It exists, again, adjacent to this particular volume. So I have the atmospheric pressure here, which is exerting a force. And then I have the atmospheric pressure here, which is also an exerting force. And just to backtrack a little bit, or just to reinforce, the pressure on the left side is exerting a force going in that direction. The pressure on the right side is exerting a force going in that direction. So again, that is the pressure energy density that happens due to the differences in those pressures. All right, so having said that, here's the cross-sectional area A2 right here. Good enough. A little cross hatch. So this is V1, P1, A1. That is the cross-sectional area of the tube at that point. The cross-sectional area at this point is right here. So this would be A2. So cross-sectional area 2 is associated with P2 and V2. Okay, so that's my pipe. The question is, how much water flows into the atmosphere during a 10-minute period? So this is the other There's really not a lot to this chapter. Let's see. We have the definition of pressure. We have the definition of mass density. What else did we talk about? We have buoyant force, how the buoyant force is equal to the weight of the displaced fluid. We have the whole notion of displacement. And all of that's kind of fluid statics. And then we have the Bernoulli principle. Bernoulli. And now we have continuity, volume continuity, and mass continuity. And I think maybe I'm forgetting some things. Oh, and then Pascal's principle. This is it. What I just jotted down here is everything I believe that's in chapter 14, Pascal's principle. All right. So we're going to talk about continuity. So the overarching theme here in this solution is continuity. Continuity means the following: what goes in must come out. And do you know why this is true when it comes to liquids? Because this is another big statement. Liquids are incompressible. You can't compress a liquid. Incompressible, which actually makes them outstanding transmitters of force. Liquids are incompressible. You can compress a gas. You can compress a solid. You can compress a plasma, but you can't really compress a liquid. And again, that makes it unique. So these are like the 4 states of matter: gas, solid, plasma, liquid. You can compress gas, solid, and plasma, but not a liquid, because think about what a liquid is. All of the particles in the liquid, all of the liquid molecules are free to slip, slide all over the place. So if there's any gaps that crop up, the liquid molecule is going to quickly fill the gap. So liquids are very good about making sure voids or cavities never form. That's what makes them incompressible. So having said that, you know what that means. Whatever. So this is where I was looking for my animation, but I will talk my way through it. So if I clear the deck for a minute, if I just take a sample volume, I'm going to take a sample volume and again, look at it as it flows through this pipe. So I'm just going to take this sample volume right here and keep my eye on it. Okay. So I'm going to take this little imaginary purple tiny volume of water. And as this purple volume of water flows from left to right, as it encounters this narrow region, it's going to basically get smaller as far as its diameter, but longer in terms of its height. So this is what my sample fluid volume looks like now. So it kind of sounds like a Kepler's second law. You know what I can say about this? Whatever the volume is here, volumes are equal. Volumes are equal. Even though they have different shapes, the volumes are equal. And why is that? That's due to the incompressibility of fluid. And you know what? Masses are also equal. Mass is also equal. So different shape, different location. But if I'm just looking at, if I'm basically saying, you know what, I'm just going to look at a 3 cubic centimeter volume. So this would be 3 cubic centimeters. And I'm just, again, keeping my eye on that same 3 cubic centimeters worth of volume. This would also be 3 cubic centimeters. Mass is also equal. Same volume, same mass. So let's just say, for the sake of conversation, maybe this is 0.5 kilograms. This would be 0.5 kilograms. So, and that's because you can't compress a liquid. You can compress everything else. So let's cough up the equation that basically says that in equation form. Well, okay, if I look at this volume right here, I know what volume is. This is basically, it looks like a cylinder. So volume is base. So it's the cross-sectional area. So I know how to calculate that area. I mean, the volume. It's going to be whatever this cross-sectional area is times whatever this distance is right here. Okay, so if I just do this, I'm gonna just set it up like this. On the left side, I have, what if I just do cross-sectional area A1 times V1? Actually, let me even go more primordial. What if I just call this X1? Okay, so the volume would be the cross-sectional area A1 times X1. That's the volume, X1. And that equals the volume over here, where this is cross-sectional area A2, and this would be X2. So whatever those volumes are, they can't change. A2, X2. And then I'm going to walk up to that expression and divide by time. Divide the left side by time, divide the right side by time. So because I want to cast this in terms of a rate. So I can do whatever I want as long as I'm not breaking any math rules. So now I'm saying A1 V1 equals A2 V2. And this has a whole special name. This is called volume continuity rate. Yeah, volume continuity. So ready? This is called RV. Volume continuity means whatever A1 times V1, and that's V for velocity, not V for volume, equals A2 times V2 equals some constant. This is volume continuity, rate of volume flow. If I walk up to this expression and divide by, or if I multiply through by rho, so I'm going to multiply this side by rho and then this side by rho, then I have something known as mass continuity. R for rate, M for mass flow rate. So sometimes I refer to this as volume flow rate. Sometimes I refer to this as mass flow rate. Okay, so if I multiply through by rho, that would basically be rho A1 V1, and we're assuming the density doesn't change, equals rho A2 V2. Just before we move on, what are the dimensions here? So if I do the dimensional analysis on here, ask yourself, rho is kilograms per cubic meter, area is square meters, volume is meters per second. So you know what the units are there? The units are kilograms per second. A kilogram per second is the mass flow rate. So dimensionally, that makes sense. If I do the dimensional analysis here, for example, I have meters squared times meters over seconds. Meters squared for area, meters per second for volume. Those units are cubic meters per second, which is basically, again, a volume per second. And this is what's known as volume flow rate. There. So this is brought to you by the incompressibility of water. And I think now we can actually start working on this problem. What volume of water flows into the atmosphere in a 10-minute period? So I know V1. All right, so I'm going to do this. I'm going to say the volume flow rate equals, and I know V1. Do I know A1? I do. Equals A1 V1. It also equals A2 V2, but I don't know what V2 is. So ready? A1 is going to be pi r squared. Pi times r. A1 is on the right side, so that's the skinnier. That's the neck portion. So 0.052 meters divided by 2. There's pi r. There's pi. Oh, this is 2.8. Sorry. 0.028 meters over 2. This is pi r squared. This is the velocity of V1. So I know this velocity is given to me as 16 meters per second. So that's 16 meters per second. You can see the dimensions are easy. I'm getting cubic meters per second, and my calculator says pi r squared, pi times r squared times 16 equals store alpha A equals the some number that is now committed to calculator memory. That's my volume flow rate. So then I'll say in 10 minutes. In 10 minutes, this is what I'm going to do. I know the rate at which this water is flowing out into the atmosphere. So I have calculator memory location A, meters cubed per second times 10 minutes. Let the dimensional analysis guide you. Times 10 minutes, I got to convert. I'm going to convert from minutes to seconds. There are 60 seconds per minute. So then if I just do the cancellation, seconds cancels with seconds, minutes cancels with minutes. So I'm going to take alpha A, multiply by 600, and get my answer. This is in 10 minutes, this much fluid flows out into the atmosphere. 5.91 and some change. And the units would be cubic meters. Okay, done with part A. So that is volume flow rate or volume continuity or just continuity in general. B, what's V2? Okay, let's get V2 very quickly. Ready. Did you know that the volume flow rate is constant because liquids are incompressible? So it's going to equal A1 V1, and it's going to be the same as A2 V2. So if I just isolate V2, this is the volume of that. And I know one thing for sure, V2 has to be less than V1. I have that insight now, and hopefully you do too. You need to be able to see exactly why this velocity V2, without doing any calculations, how that has to be less than this velocity. This velocity has to be greater because it's dealing with a skinnier volume, basically. All right, so then I'm going to say V2 is equal to A1 V1 over A2. And then get your answer for that. A1 pi r squared. Remember that V1 is velocity, not volume. So pi r squared divided by pi r squared. V1 is the skinny volume, 2.8. Okay. I'm going to put this in calculator location B just in case I need it. That's part A and part B. Now we have to talk about something called gauge pressure. Gauge pressure. Here's gauge pressure. P subscript G is gauge pressure, and it's the pressure difference. It's the pressure difference with respect to the ambient or surrounding pressure. That's what gauge pressure. So when you go check the tire pressure in your automobile wheel, your automobile tire. You are that gauge pressure, or that when you check that pressure, it's spitting out a number that represents the pressure above the surrounding atmospheric pressure. That's what gauge pressure is. It's the difference with respect to the surrounding pressure. So let's do Bernoulli to get the gauge pressure. Do I need Bernoulli? I do, I think. Okay, so number 5. Here's Bernoulli. So this is energy state 1 right here. No, this is energy state 1 right here. The narrow pipe, energy state 1. The wider pipe, energy state 2. Here comes Bernoulli. Ready? Pressure energy density plus kinetic energy density plus gravitational potential energy density equals pressure energy at energy state 2 plus kinetic energy density plus gravitational potential energy density. But there's a lot of low-hanging fruit because this is a horizontal, and don't get too complacent. Don't always think that it will not always be a horizontal pipe. In fact, maybe the only time you see a non-horizontal pipe is on exam 3, but it's not a big deal because you're accounting for it right here. But this is a horizontal pipe. So this term and that term basically cancel each other out. This term, P1, is the atmosphere because our streamer at energy state 1 is exposed to the atmosphere because of the givens. We know that water is squirting out into the atmosphere at energy state 1 there. What else do we know? That's it. So we need to figure out the gauge pressure. So here's the gauge pressure. I got to ask myself, where do I have the higher pressure? So I'm going to have this whole conversation again. Well, this is low. Relative V2 is slow relative to V1. So slow flow means high pressure. Fast flow means low pressure. So this is my way of saying the pressure at 2 is going to be greater than the pressure at 1 because of conservation of energy. Slow flow, high pressure. Fast flow, low pressure. P2 is greater than P1. So I'm going to do P2 minus P1. That's going to be my gauge pressure because I know P2 minus P1 is some positive number. If you didn't know to do that, you'd still get the right answer, but you'd have a negative, which you could argue isn't the worst mistake to make. But I know P2 is greater, so I'm going to say P2 minus P1, and then just do algebra on number 5. P2 minus P1 equals 1/2 rho V1 squared minus 1/2 rho V2 squared. And I can pull out a common factor. Oh, and this is my dollar sign. This is dollar sign. And I know P1 is equal to atmospheric pressure. But I guess I don't even need to, I don't even really need to note that. I'm just saying, yeah, P1 is my atmospheric pressure. So that's why it is this difference. It is the pressure difference with respect to the atmospheric pressure, which I'm noting right here. That's my dollar sign. So then if I pull out a common factor, 1/2 is a common factor. Rho, this is what? Is this water? Yeah. And here's the density of water. The density of water is equal to 1,000 kilograms per cubic meter. So it's 1/2 times 1,000 kilograms per cubic meter. That's a common term. So then here's V2 squared. No, V1 squared. V1 squared is, for me, it's given. It's 16 meters per second squared minus V2 squared. And V2 for me is sitting in memory location B. And let's get an answer for the gauge pressure. we're doing all of this sleuthing to figure out, hey, what's going to be the pressure difference at V2 with respect to at 2 versus 1. A big number equals 117, 239. Okay. What are the units here? You know what? If you did the dimensional analysis, you're going to have to make sure you get a Newton per square meter, because we are expecting a Newton per square meter or a Pascal. All right, so that's another, so that's continuity along with Bernoulli. Okay, so Venturi meter, which again is basically a pump. This is pump action. It's behind a lot of practical applications. The one that I first think of is just regular water pumps and carburetors, like the carburetor on your lawnmower. Automobiles used to have carburetors, but I think the last carburetor was found in a production automobile like literally in 1985. Now it's all fuel injected, but still the principle is still widely exploited for a lot of practical applications. So just like a pitot tube was used to measure airflow speed in an airplane, a Venturi meter kind of does the same thing. A Venturi meter measures fluid flow speed in a pipe. Just reading this statement. A Venturi meter is used to measure the flow speed of fluid in a pipe. So what you see here is pretty self-explanatory. We have a wide region, and then we have a neck region or a narrowed region. In fact, just because we are doing good on time, let me demonstration of let me just see if I oh this guy's good. I really like this guy. This is good. It's always fun to watch TV. Let's watch a little bit of TV. I don't know. This guy is very kind of relaxed. This is like my ASMR fix right now, but he does a good job. So here is our friend demonstrating the Bernoulli effect, which is the Venturi effect, basically. Those are kind of synonymous terms. Here goes.
This is a Venturi tube. I've got a source of air that'll come in to this side of the tube. It'll pass through this region where the tube is wide, and then here where the tube is quite narrow, and then back to wide again. Since the same amount of air has to pass through this wide cross-section as passes through here, namely the volumetric flow rate has to be the same. The number of cubic centimeters per second passing this spot has to be the same as the volumetric flow rate that passes this spot. And because this spot has a smaller cross-sectional area, the air has to flow faster here. So we've got a high velocity region here, a low velocity region here. But Bernoulli's principle says that the higher the velocity, the lower the pressure. So in this spot here, contrary to what your intuition might say, instead of the pressure being high here, the pressure is actually low. And we can demonstrate that using this colored water. I filled the bottom of these this U-shaped glass tubing with water that has a little bit of food coloring added to it. What you'll see is when we turn on the air, this column of water in the middle will rise because the pressure here is lower and essentially acts as a suction for the water. So this one will rise higher than either the other two.
Pretty good.
So that's a Venturi tube, a demonstration of Bernoulli's principle, and very important in a lot of areas of fluid dynamics.
A good visual on what a Venturi meter is, which again was based on the Bernoulli principle. Let's figure out, we need to figure out what is the flow rate. So this is the as I'm reading through here, let me just go to the punchline. What is the rate in cubic meters per second? So this is the dollar sign. The dollar sign, all of this is basically volume flow rate equals the dollar sign. Okay. So I'm just going to do some preliminary setup. I'm going to call this region 1. This is region 1. This is region 2. And I have a whole lot of information. I better do the read through here. The meter is connected between two sections of pipe where we know the cross-sectional area A of the entrance and exit. Between the entrance and exit, the fluid flows from the pipe with speed V and then through the narrow throat with a speed little v. A manometer, this is the manometer. And if you're wondering, why are we never really paying attention to the manometer? The answer is we are, basically. The Bernoulli effect takes into account this. Well, takes all this into effect, but this is showing what this last demonstration just featured. Fast flow, low pressure. Low flow, high pressure. So I can see right here, I can see that I know just very quickly, I know, and hopefully you know, or will come to know, you know that this is low velocity, high pressure. So this is high pressure over here in this region at the entrance. This is low pressure because I know the fluid velocity. I know the flow velocity has to increase because I have this constriction. Whatever, because of continuity says, hey, if things can't get backed up, if this liquid is incompressible, you can't compress anything, you can't back up, you can't queue up like, attendees waiting to get into a crowded movie theater. It has to go. It just has to flow. So that is accommodated by having this attain a high velocity relative to this velocity. So this is high velocity, low pressure. And you can see that by this manometer. You have this height difference because this is low. If this is low pressure here and this is high pressure here, that explains why this pressure is pushing down with a greater net force compared to this pressure. I mean, in both cases, you have the pressure here. This pressure is pushing down. This pressure is pushing down, but this is the higher pressure compared to that. So that's pressure work. So Bernoulli accounts for this difference in pressure. Okay. So the change in the fluid speed is accompanied by a change in pressure, as I just rambled on about, which causes a height difference per previous statements. Here, delta P means the pressure in the throat minus the pressure in the pipe, although they told us that, but we would go ahead and just figure that out anyway without being told. This is fresh water, and we know these cross-sectional areas, and we know the pressures, the relative pressures. What's the flow rate? So here goes, ready. Bernoulli says pressure 1, pressure energy density plus kinetic energy density plus gravitational potential energy density, rho GY1, equals pressure energy density in the throat plus kinetic energy density in the throat plus gravitational potential energy in the throat, low-hanging fruit, horizontal pipe. Again, and I am kind of cringing because I just need to remind you, don't assume it's always going to be a horizontal pipe, but these do cancel. Anything else? Nope. But I do know a lot of numbers. So I guess my thinking is to go after velocity. Try to isolate. Try to find V1 and or V2, because if I can find V1 and or V2, I'm going to be able to find the volume flow rate. So this is my strategy. So I'm going to say, well, let's see. If I do, so this is the higher pressure. So I'm going to do P1, P1 minus P2, P1 minus P2, because I know P1 is my greater pressure. Okay, so P1 minus P2, and I'm looking at equation number 1, equals 1/2 rho V2 squared minus 1/2 rho V1 squared. So that's me just doing some pretty basic rearranging of step 1 there. Okay, so number 4, delta P. I do know, do I know delta P? Delta P. I don't know delta. Oh, I don't know, but I do know, I do know P1. P1 is my high pressure. So that's the 51,000 pascals. I can just leave that as Pascal. Minus P2. So this is P1. P2 is the throat pressure. That's 44,000 pascal. So Pascal is a Newton per meter squared, equals 1/2 rho. And this is water, isn't it? Yes. It is, yeah, fresh water. All right. So the density of fresh water is 1,000 kilograms per cubic meter. So 1/2 of that is just going to be 500 kilograms per cubic meter. That's a common factor times V2 squared minus V1 squared. So this, I'm officially at a dead end. So this is the always anticipated moment of panic. So now let's do continuity to the rescue. Continuity to the rescue, which means the following. Because water's incompressible, as are all liquids, I can say, well, the volume flow rate, A1 V1 in region 1 is the same as the volume flow rate in region 2, and this equals a constant. So again, that's continuity, and specifically this is volume flow rate. So from this, you know what? I'm going to basically just say V1, therefore, can be just written as A2 V2 all over A1. Okay. Let's get a number on that actually right now. It'd be easier if we do it. Not right now, I guess. Well, I'm going to do A2 over A1. A2 is the small little teeny tiny area. So this is going to equal 37 square centimeters is the area of A2, which is right here, the throat. That's the throat cross-sectional area. That's given to me. The pipe, or the wide portion cross-sectional area, is 74 cubic centimeters, or square centimeters, I should say. And you can see right away, I don't have to convert. Because I can cancel these out, there's no need to convert. So I have V2 times V2. So you know what I'm going to do? I'm just going to say V1 equals calculator memory location A times V2. So let me get that. I'm going to do 37 divided by 74 is 0.5. That works out pretty well. Is it? All right. Well, I don't even need to store that. I'm just going to say V1 equals 0.5 V2. So number 8, I'm going to go back to number 4. Here's my new number 4. Ready? 51 minus 44 is 7. So I have 7 times 10 to the third pascals, 7,000 pascals, because 51 minus 44 is 7, equals 500 kilograms per cubic meter times V2 squared, V2 squared minus V1 squared. And here's V1 squared. V1 would be 0.5 V2 squared. So that is my new number 4. All right, so my next step will be solve for V2. And then step number 10 will be the volume flow rate is just going to be A2 times V2. And you know A2 is given. A2 is given as, for me, A2 is 37 square centimeters. And you have to think about converting. You have to end up with cubic meters per second. So make sure you don't forget about converting. And V2 is what you just got from here. Let's get this answer then. We'll do one. We'll take some time on this. Take your time on this, and I'll get the next one set up.
This is a Venturi tube. I've got a source of
Sorry. Okay. $14.6. Well, no one's done with this yet, so I guess I should wait. In fact, some people haven't even started. I think, unless maybe I'm not looking at things right. Well, I'm going to plow ahead and let you guys stop me or interrupt and ask questions.
I'm just finishing up the math.
Okay, so I'll wait a bit longer then. I think what I'll do, you guys, is let's move on. Levi's done. Everyone else is still hammering away, which is fine. But in the interest of progress, let me add some stoppage time. So again, I'll make sure chapter 14, quiz 6 is open until whatever, 5 o'clock, 6 o'clock, whatever it takes. But just so we can keep moving forward, because I think at this point, you guys are probably just mired in the math minutiae, which is important, but you guys can handle that during stoppage time. So let's go on to chapter 14, quiz 7. And again, come back, give yourself a little time out for quiz 6, go to quiz 7, just so you don't compound the issue that you're going to fall behind on quiz 6. And then now you're going to fall behind on quiz 7. So don't let that happen. Let's just start quiz 7 right now. This should be quiz 7, our last quiz of the day. So here it goes. This is a pipe. All right, so fresh water. So right away, I know rho equals 1,000 kilograms per cubic meter. Fresh water is flowing horizontally. All right, so I'm going to draw a horizontal pipe. Here's one side of the pipe over here. And then maybe here's the other side of the pipe over here. And you can see, well, this is what the pipe looks like. This is what the pipe looks like if A1 equals A2. So this is cross-sectional area A1. This is cross-sectional area A2. If A1 equals A2, that's what the pipe looks like. If A2 is less than A1, then the pipe looks like this. And I have this narrowing. I have a pipe that's narrowing. So then this is what this pipe would look like in the case where A2 is less than A1. like that, and like that. Okay, good enough. All right, so this is cross-sectional area A1. This is cross-sectional area A2. This is a horizontal pipe. So once again, it is a horizontal pipe, right? Like that. Horizontal pipe, water's flowing horizontally from section 1 into section 2. And then I have a plot. I have a plot of pressure difference. So let's see, on the left side, this would be cross-sectional area A1. It's associated with a pressure, some pressure, and some velocity. So my velocity, my flow velocity, I'll just indicate like this. This is my flow velocity. Okay, this is V1. And then over here on the right side, I have cross-sectional area 2 associated with pressure 2. And I know one thing, I know this velocity over here, I know V2 is, in this case, for this particular pipe situation, I know that this is V2. And this is for the pipe, this is for a narrowing pipe. And I might have a narrowing pipe, I might have a widening pipe, just looking at the graph. All right, so this is what I have going on. And now I think it's time to talk about what this graph is saying. I have a graph here showing this delta P, P2 minus P1, that's on the y-axis. And then on this axis, oddly enough, this sounds like kind of tortured, but I have 1 over A2 squared. All right, so the points that kind of stand out to me are this point, that looks like a crispy intersection. So does this. So does this. So let's have the conversation here. I'm gonna have a long drawn out conversation about what this particular point is saying. At this point, let's see. At this point, P2 minus P1 equals 0 at that point. So you know what that means. That means P2 equals P1. And you know what that means. The only way that can happen is if A1 equals A2. So, aha. I now have a value for A2. A2, which is constant, A2 doesn't change. Cross-sectional area A2 doesn't change, but A1 does change. A1 equals variable. How do I know that's true? Because you can see A1 can be as small as 0 or as great as 34. Well, I should say 1 over A1 squared. 1 over A1 squared. It can never really be 0. So that's well, hang on. Let me rephrase. No, I think that's right. Yeah. So A1 varies. A1 varies from this value all the way to this value. So at this particular point right here, the point that I'm looking at right now is the point that shows 1 over A1 squared equals 17. All right, so let's go with that. A1 equals a variable. That's true. At this particular point, I know I better start numbering things. All right, so number 1. When P2 minus P1 equals 0, which is this point that I keep referencing. At this point right here, I know the following. I can say that 1 over A1 squared equals 17 meters to the negative fourth. Right. All right. So you know what that means? That means A1 squared equals 17 meters to the fourth. Let me just make sure I got my head screwed on straight. 1 over A1 squared equals, oh yeah, 17 meters to the fourth. So I did not have my head screwed on straight. 1 over A1 squared equals 17. All right, that looks good. So therefore, A1 squared equals meters to the fourth power over 17. That's better. So therefore, I can say the following. I can say A1 equals the square root of 1 over 17. And when I square root meters to the fourth, I do get square meters, which is something I would expect. And this value equals A2. And I'm just going to make the note again. A2 is constant. So I know the official value of A2. A2 is constant. A1 is variable. I'm just sort of saying what's going on when A1 happens to have that value. A1 is variable. So I'm just repeating this. So I'm going to put that in memory location A. What is 1 divided by 17, the square root of that? That's sitting there in memory location A. Oh, and that's the answer to part A. So I just found out the answer to part A because it says in this situation with this pipe and this data from the graph, what's the value of A2? So I just did that. So I am done with part A. And I'm going to store this in calculator memory location A. So 1 down, 1 to go. Part B says, what's the volume flow rate? So all of this is number 1. Number 2, this is how we write volume flow rate. It equals A1 V1, and it also equals A2 V2. Well, what to do? This could be a job for Bernoulli because I'm not seeing any volume or any velocity information. So this is my $sign. So to get to my $sign, I guess I'm going to have to go through Bernoulli. P1 plus kinetic energy density plus gravitational potential energy density equals pressure energy density plus kinetic energy density plus gravitational potential energy density. Low-hanging fruit. Is there any? Yeah, it's a horizontal pipe. And do I know? Well, I'm going to look, I guess, pardon me. I guess it's time to look at the graph again. Look at P2 minus P1 equals this value right here, because I have an easily identifiable data point. When P2 minus P1 equals this value right here, which in that value right there is 290,000, so 290 E3 newtons per square meter. That's P2 minus P1. And at that point, I know a value for A1. 1 over A1 squared equals 34 meters to the fourth. That's why I'm choosing that point. This point gets me that A1. A2 is fixed. A2 is not changing, but A1 changes. And I'm looking at the situation when 1 over A1 squared equals 34 meters to the fourth. Okay. So that's the point I'm looking at. So how can I, well, I'm going to keep going here. if I look at that point, then I'm going to say A1 equals secant B. Yes, A1 equals, and I better show the work there because from the graph, I'm just going to repeat this, 1 over A1 squared equals 34, actually meters to the negative fourth, sorry, and this should be negative fourth. So therefore, A1 squared equals 1 over 34 meters to the fourth. And this is where I'm getting A1 equals whatever it is. I'm going to put it in calculator memory location B. Okay. Store alpha B. Let me redo that. Okay, I have that. Oh, no, I don't. Oh, I just stepped on my A. Let me redo A1 divided by 17. Okay. Onward. All right, so I'm going back to Bernoulli, number 6, back to number 3. So here's what number 3 is now. I can put number 3 into this form. P2 minus P1. P2 minus P1, looking at number 3, P2 minus P1 equals 1/2 rho V1 squared minus 1/2 rho V2 squared. And once again, I'm looking at the point where P2 minus P1 equals 290. I'm looking at this point right here. So number 7, P2 minus P1 is going to be 290,000 Pascal equals, here's the common term, 1/2 times rho is water. So it's 1/2 times 1,000 kilograms per cubic meter. And that's a common term. And then I'm going to pull. So we've seen this before. V1 squared minus V2 squared. Okay. So I need one of those volumes to figure out the volume flow rate. Number 8. Here goes. I'm going to do the old volume flow rate is A1 V1 equals A2 V2. So this is what I'm going to do with continuity, specifically volume flow rate continuity. I am going to say V1 equals A2 all over A1 times V2. So number 8 gives me that substitution I can use for V1. V1 equals A2 V2 over A1. Okay. So here's my, I'll go over here, number 9. 290,000 pascals equals 500 kilograms per cubic meter times V1 squared. Here's V1 squared. It's A2. All right, so A2 over A1. It's A2, which is calculator memory location A. There's A2. Yes. Here's A1. A1 is calculator memory location B. So that's A2 over A1 times V2, and I got to square it. This whole thing gets squared minus V2 squared. And let me see if I have my head screwed on straight. So I am saying, well, this really in calculator memory location A, for me, I have A2. Calculator memory location B, I have A1. A2 over A1 times V2 is what I just said right here is equivalent to V1. So I think that's correct. I'm just going to check my memory, calculator memories. Is that alpha A and is that alpha B? All right, so those are looking good. Number 10.
Hey, Professor.
Yep.
The first thing we saw for A, that was A1, right? Because we did
In
A1.
part A of this, we said A1 equals 1 over the root 17 square meters. And that actually also equals A2. And then, so this is the work, and then I put that in memory location A. This is the work that I went through to basically say, this is the value for A2. Because here, when P2 minus P1 equals 0, right here, that's just saying, well, I know what A1 is, and then from that I can get A2. So that's where A2 came from. So this is cross-sectional area A2. So this is me saying, I know what this cross-sectional area is, and that's what I put into memory location A, and that is the answer to part A.
Okay.
Yeah, it's tricky. It's involved for sure. All right, so then I'm going to solve for V2. Step number 10. I'm going to do 290,000 all over. I'm going to drop the units and do dimensional analysis as a whole sidebar effort. 290,000 over 500. Yes, equals V2 squared. That's a common factor. And then it's going to be memory location A all over memory location B. This whole thing squared minus 1. So we're going to get a value, number 11. We're going to get a value for V2, and we can do that right now. 290,000. Yes, right. Okay. V2 now is sitting here safely tucked into calculator memory location C. I'm going to redo that. Okay, that's 57 square root. I'm getting the same answer twice, always a good sign. And now, to conclude, the volume flow rate is equal to A2V2. It's also equal to A1V1, so take your pick. But I'm just going to go with A2V2. So here's A2, A2V2. A2 is still sitting there in calculator memory location A, and V2, which I just solved, is sitting here in calculator memory location C. So what is alpha A times alpha C? 5.84 and some change. 5.841 and some change, and the units better be cubic meters per second. That's it. That's the answer to part B. Let me do this. So no hurries, but I will ask you guys, because I think 7 quizzes is enough for one day, and it is 4:16. Any before I sign off, any requests for extensions for any one of these quizzes? 1, 2, 3, 4, 5, 6, or 7.
Yeah, I gotta find it real quick. It was
Say again.
Yeah, I think maybe the first one. Give me a second, real quick.
Yeah, I was gonna ask for 1, 3, and then you said you do for 6 as well.
Yeah. All right. So quiz 1,
Quiz 1, yep.
quiz 1, quiz 3, quiz 6. Is that it? So if that's it, and feel free to shout out if that's not it, I will extend these quizzes to let's see. 1, 3, and 6, you're saying it's now 4:17. How about 5 o'clock? Is 5 o'clock okay?
It's good with me.
Okay. All right, you guys. So we'll see you on Thursday for an exciting lab and thrilling demonstrations. And give me a minute to just adjust quiz 1, 3, and 6 until 5 o'clock.
Do we have any more of those homemade templates we have to make on Word for Thursday or no?
Homemade templates?
Yeah, remember that Thursday for the lab.
No. Refresh my
We
memory.
turned in the Word document on Thursday. It had we made a template from our lab sheet. We made it in Doc.
You mean for the solar system simulation?
Yeah.
What about it?
I was wondering if we're gonna do another one of those things where we make another Word doc.
No. Why do you want to?
No, I was curious. I wasn't sure if that we're just making that a habit now, or if that was.
No, I mean, although that's a very, in my humble opinion, that's a very important skill to have. It's very helpful to be able to do that kind of documentation. You might not like it. Maybe you like it, maybe you don't. But I think that there's no plans to do any type of formalized approach like that. Although, I mean, food for thought. So I'm glad you bring it up. Yeah, for sure. I mean, you have no idea how that's going to benefit you. And again,
Yeah, I
I
know.
always say it doesn't matter if I like it or don't like it. If I'm committed to my path, then stuff like that I just master.
My dad was always big on like being good with Excel and OneNote,
Yeah, I
Word,
mean,
all that kind of stuff.
you have no idea how many doors that can open. If you are pretty even, Steven, with people to the left of you or to the right of you, but you know those skills, you win. So it's funny how that works. Yes, I'm glad you brought that up. All right, so give me again a minute to extend 1, 3, and 6, and we'll look forward to seeing you on Thursday. Goodbye.